Okay, this is a video for high-level maths. This is about improper integrals, specifically the type that have an upper limit of an infinity. An improper integral is an integral that has some kind of infinity in it, right? You can't find the area under the curve if that area is going to go on forever and ever and ever. However, but that can happen if you've got one of the limits set at infinity, so this is from 0 to infinity, or the lower limit as infinity, or both limits as infinity. The other way you can do it is you have some kind of discontinuity or some kind of asymptote in the middle, so some point in the domain, that should say, some point in the domain or between the two limits of integration is heading towards infinity. For example, integral of 1 over x from -1 to 1 is improper because when x equals 0 you have an asymptote, so it goes to infinity on both sides. It goes to infinity from the positive side and negative infinity from the negative side. So that's improper integrals. We're going to focus on the first type here, where you've got a positive lower limit, or doesn't necessarily have to be positive, but a definite lower limit, and a infinite upper limit. We'll take a look at how the others work with respect to this one. Can you actually find this area? That's, I suppose, the major question. Well, you can, to a degree, and this has to do with convergence and divergence. You would have covered this a little bit when we did geometric series and sum to infinity, and we talk about how they converge at a point. If you look at it diagrammatically, here's some very professionally drawn diagrams, that graphs that I drew. But say you have a function that looks like this, and as you keep going towards infinity, this curve becomes asymptotic to the line, so the area there becomes infinitesimal. So really, that area you keep adding such a fine infinitesimal amount that it really doesn't make any difference. So it converges on a finite number. Okay, divergent would be something like this, where the area just keeps bigger and bigger as x approaches infinity. Okay, so convergence will occur if if it's a continuous integral, if there's no discontinuity, the function is continuous between a and b, and this is the important thing to remember here. The limit as b approaches infinity of the integral between a and b of f of x with respect to x is finite. Okay, we can't find the integral between a and infinity, but we can find the integral between a and b, and we're just going to make b approach infinity. So that's the theory. Here's two examples. Pretend you don't know this is going to be convergent yet, but let's have a look at this. So we got the integral from 1 to infinity of 1 over x squared dx. If we can't do infinity, but if we look at the limit as b approaches infinity of the integral from 1 to b of 1 over x squared with respect to x. Now we take the integral of 1 over x squared, that's -1 over x, and our limits are b upper limit and 1 lower limit. We've still got our limit sign here. We substitute in those limits, so that shouldn't actually be there. So we've got -1 over b minus -1 over 1. If we simplify that a little bit, so minus negative, that'll be 1 minus 1 over b. And if we substitute in a limit, that's 1 minus 0, so it's 1. So it's converging to a single numerical answer. It's converging on 1. Here's an example of a divergent. Okay, it looks very similar, but it's the integral from 1 to infinity of 1 over x dx. And if you know what these look like, they do look kind of similar as well. But let's go through the process. Okay, the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. Okay, the integral of 1 over x is ln x between the limits of b and 1. Okay, so I substitute in b and 1. So the integral of 1 over x between 1 and b is ln b minus ln 1. You know that the natural log of 1, ln 1, is 0. So it's limit as b approaches infinity of ln b. So substitute in infinity, we get ln infinity, which is, of course, undefined infinity. So this is just divergent. It just keeps getting bigger and bigger. Now, if we look at those two things, they're very similar, but this one's convergent and this one's divergent. If you think of what they look like, and if you think of what their curves look like and the area under the curve, there's not really big difference between these two, but there's a large difference in whether they converge or diverge. So there's a large difference in the area underneath them. And this has to do with how quickly the x is decreasing. Just to prove this a little bit more, I can confirm this on my calculator. If I do the limit between 1 and a big number of 1 on x, I get 9.2. If I do the same thing for 1 on x squared, I get 0.999. Now I'm going to put in even a bigger number, and this is where we get a little problem because it's questionable accuracy, but basically 0.999, 1. So it's converging on 1. This just seems to be getting bigger. It's getting bigger very slowly. It's taken several million to get up from 9 to 23, but it is just getting bigger. So this is 1 on x, the integral of 1 on x to infinity is diverging, but 1 on x squared is converging. That makes me think, okay, we've had 1 on x, that's divergent, 1 on x squared is convergent. What about other numbers where p is a real constant? Okay, just by the way, if it was, instead of 1 on x, if it was just x, or 1 on x to the p, if it was just x to the p, it's always going to be divergent. And just think of that, okay? Y equals x, it's always increasing. Y equals x squared, it's always increasing if we go from 1 to infinity. Just look at what the graph looks like and think about the area underneath. You'll see that it's always increasing, so it's always divergent. Okay, let's see what happens with the integral of 1 over x to the p. Okay, this time we put, again, the limit as b approaches infinity of the integral between 1 and b of 1 over x to the power p dx. Just to make it a little bit simpler, we'll, instead of 1 over x to the p, we'll do it x to the negative p. Integrating that, you add 1 to your exponent there, and you divide by that value. Just rearranging this to make it look a bit neater. I don't want like negative exponents, so I'll negative both of those and put them on the bottom. So it's 1 over, instead of minus p plus 1, we do 1 minus p. And instead of x to the negative p plus 1, it's x to the positive p minus 1. Okay, that's just rearranging, no integration there, that's just rearranging. Okay, now we can substitute in our b values. No, first of all, we'll take out this constant, because 1 minus p is just a constant, because p is a real constant. So I'll take that outside. Now we can substitute in our b values and our 1 value. So we get here 1 over b to the p minus 1, and this is a mistake, this is 1 over 1. 1 over 1, which is 1. So there we go, that's u constant at the front, and limit as as b approaches infinity of 1 over b to the power of p minus 1 minus 1. Okay, we can't simplify any further, but let's look at that. If p is greater than 1, then this value here, the 1 over b to the power p minus 1, will be 0. Will approach 0 anyway, because it's going to be 1 over infinity to some kind of positive power. So therefore we'll have 0, we'll have minus 1 here, so the integral will just be minus 1 over 1 minus p, or if you want it would be 1 over p minus 1. Meaning, and because they're all constants, 1's a constant and p's a constant, you've got a convergent integral. We had this one before. If p equals 1, then you've got 1 over x, so we know it's going to be divergent from the last slide, but it is because you've got power of 0 here, so that's 0, so you won't have any b's, so that's 0 and that's a minus 1, but you'll have 1 minus 1. You'll have undefined in your constant value at the front. If p is less than 1, then this power up here, p minus 1, is going to be a negative value. And so you'll have, instead of 1 over b to a negative value, you'll have b to a positive value. And that, when you put, so you'll have infinity to some positive value, meaning it's infinity. So it'll be divergent. So there's the theory. 1 over x is divergent, 1 over x squared is convergent, 1 over x cubed is convergent, 1 over x to the 4th is convergent. Okay, anytime that power there is greater than 1, it's convergent. If it's equal to or less than 1, it's divergent. Okay, that'll be useful later on. Okay, so that's a little bit complicated, but I hope you can follow that logic here. Ignore this mistake. I'll fix that up, and maybe remake this video with that fixed. But yeah, I hope this has been helpful to you and you understand a little bit more about convergent and divergent improper integrals.